So, good evening, sir. Uh, I am Pranjal Minocha, and this is my video PPT submission. So, just a second, I'll turn my laser pointer on. Yeah. So, I am Pranjal Minocha, and this is my video PPT submission for PHM 314, which is microprocessor and peripheral devices. The topic for my presentation is telescope automation using 8085 microprocessor and Python. So, this would be the workflow that we would follow. First, we'll retrieve the astronomical coordinates of a given celestial body. Then we'll use these coordinates to calculate the angle which we have to rotate the telescope and eventually the stepper motor rotations. Then we'll use the 8085 microprocessor to control and rotate the stepper motors. So let's first understand how astronomical coordinates work. So in the little image that I've shown here, we can see that the coordinate of a star is defined by two angles. One is azimuth and second is altitude. This is happening because we have made constant the zenith and the true north, and they are and altitude and azimuth are defined on the basis of zenith and true north. So this is known as the horizontal coordinate system, and this uses the observer's local horizon as the fundamental plane to define the two angles. So azimuth can be seen as from the image we can see it. Azimuth is the angle between the star's position vector, its projection on the horizon plane, and the true north. That is the angle azimuth. And altitude, as we can see, is the angle between the star position vector and the horizon plane. So now that we understand how astronomical objects can be located using just two angles, we can now come to understanding stepper motors. So stepper motor converts digital pulses into precise angular steps of desired value. The GIF shows how the stepping action is conducted in a stepper motor. The sequential switching of supply causes the reversal of magnetic polarity without actually reversing the polarity of the supply. So we use a four-step input sequence, which is also shown in the GIF here, which gives us an accuracy of around 1.8 degree per step, and which is also the least count for our stepper motor. And our setup will require two stepper motors to control the azimuth and the altitude angles respectively. So now we come to the code part. I have used AstroPy library in Python to retrieve the all-task coordinates, to retrieve the real-time all-task coordinates of the Andromeda galaxy. So instead of Andromeda, I could have written anything like IM33 galaxy or anything else, and the code would have given me the coordinates of that given celestial body. So first I've imported the required libraries that are AstroPy and DateTime, and then I've stored the universal coordinates of Andromeda in a variable coord. Then I've initialized the location. Then I've initialized the location and time where the observation will be made, and the time at which it would be made. So the location is Roorkee. I've set the latitude and longitude values, and also the average height above the sea level of Roorkee, and stored it in an Earth location object. And also we are 5.5 hours above ahead of GMT, so I've also converted time into IST. So after date time and location, I have defined a frame object to which I have transformed the universal coordinates and retrieved the all-task coordinates of Andromeda at Roorkee at the time of running this code. So I've inputted location, that is Roorkee, and time, and then I have transformed this coordinates to the frame that I want. So this gives me the all-task coordinates, and as we can see here, I've outputted the all-task coordinates. The altitude angle is 57.096 degrees, and the longitudinal angle is 301.06 degrees. So after getting these angles, I have now calculated the number of iterations of the four-step sequence that are required to point to Andromeda. So the angle covered in each step is 1.8 degrees, which is the least count for our stepper motor, which sums to 7.2 degrees in each sequence. So the number of iterations for both stepper motors that we have got will be the input to our 8085 code. So the output shows that the sequence will have to be iterated 8 times for the altitude stepper motor and 42 times for the azimuth stepper motor. So now we come to the ALP code, the 8085 ALP code, which is required to move the stepper motors. So first we initialize all the ports into the B register. And no, we first initialize the port and then we input the number of four-step iterations into the B register. After performing the four-step sequence, which is in the start to call delay, we decrement value of B and we run the code and we run start till B gets to 0 and then we halt the program. So after the execution of the whole program, the telescope will point to the celestial body as the code execution completes. So now that we have understood how to carry out the automation, I would like to state some advantages that an automated telescope system would have over a manual one. So first and the most important is that automation would drastically reduce the response time and observational times. So what this means is that if you want to observe a specific celestial body, for example M33 galaxy, we just need to input M33 into the code and the telescope points to the galaxy almost immediately. On the other hand, if a human was to be operating this, they would have to first open a sky map for the particular location and then search for coordinates of M33 for the specific time and date, and then point the telescope manually to the coordinates. So this has a lot of room for error, and the pointing itself requires expertise in the instrument. The automated one, however, has little room for error. The only error that I could think of was due to the least count of the stepper motor, that was 1.8 degree. So if we were to employ a more precise stepper motor, the error would reduce. Another advantage that I could think of was that they can be operated in difficult environment where it could be difficult or expensive for humans to operate. Automatic solutions are usually cheaper and more reliable in these scenarios. So that is all from my side. This was my video PPT submission for PHN 314 microprocessor and peripheral devices. Thank you, sir.